Hello, I'm Peter Hayes. I'm the presenter of today's webinar on multi-axial fatigue life prediction, and specifically on the fatigue analysis of multi-axially loaded components in nCode DesignLife 11. I'm responsible for the development of fatigue analysis methods in nCode DesignLife. Before that, I was product manager. Okay, so this is the agenda for the webinar. First of all, we're going to consider what is multi-axial loading, how can we quantify it, and why does it matter. We're then going to look in detail at the methods implemented in nCode DesignLife version 11 that address multi-axial fatigue, and particularly using the local strain approach. So, what is multi-axial loading and why does it matter? I'm going to make an important distinction here. Many components and structures are subject to complex multi-axis loads. That is, they experience loads from different sources and directions, often with phase differences between them. However, what drives fatigue is the local stress state variations that arise due to the superimposition of the stress variations arising from the various applied loads and the geometry of the structure of the component. So if we want to know if we have a multi-axial fatigue problem or not, we have to look at the local stress history, which is going to be a stress tensor as a function of time, and to look at that in the most critical locations. We're not looking at just at the external loads. So when I talk about loading in the rest of this presentation, I'm going to be talking about the stress state variations, not the external loads. So the next few slides are about how we can understand and quantify multi-axiality. Stress is best described as a tensor, but we can always reduce that tensor to a knowledge of the principal stresses and their directions. In a 3D case, in the general 3D case, there are three principal stresses, but a lot of the problems that we face are actually 2D. For example, on the free surface of a component or on a thin sheet, we have a two-dimensional state of stress, and we only need two principal stresses. So let's consider a really simple case. A thin sheet loaded uniformly in tension along the edge. In this case, the principal stresses are lined up with the edges of the sheet, and sigma 2, which is the smaller of the two principal stresses, is 0. I'm also going to define a ratio which we'll call the biaxiality ratio, and this is the ratio of the smaller to the larger of the principal stresses. So in this really simple case, the biaxiality ratio is 0, and this special case is called uniaxial loading. Now, if we impose some variation on the load P, the biaxiality ratio will remain constant. In this case, it will be constant at 0, and the principal axes will remain fixed in direction. And this is what we call a proportional loading. So let's consider another simple example. This one is a spherical balloon. So in this case, the membrane stress in the balloon is equal in all directions. And what we have here is an equibiaxial loading where the biaxiality ratio is +1. So if we then add in some pressure variations, that biaxiality ratio is going to stay fixed at +1, and this is a proportional loading too. Okay, so let's look at another example. Let's take our simple sheet from the first example, and we'll wrap it round to make a cylinder, a thin-walled cylinder, and then we'll apply a torsional load to it. This creates what we call a pure shear stress state. The principal stresses are inclined at 45 degrees to the axis, and the biaxiality ratio is now -1. The principal stresses are equal and opposite to one another. If we then apply a varying torsional load, all the stress components and hence the principals will vary in the same way, and so this again will be a proportional loading with a biaxiality ratio of -1. This is a classic torsional fatigue failure. It's a front coil spring from a passenger car. It's actually from my car, and the crack you can see in the right hand picture has formed in opening mode on one of the 45-degree planes, and it gives a very characteristic shaped fracture surface. So now let's make things a little bit more complicated. So I'm going to go back to my thin-walled tube example, but now let's consider the effect of two load cases, tension and torsion. The tension case will generate a uniaxial loading, that is with the biaxiality 0 and the stresses lining up with the axis, and the torsion case will create a pure shear loading, biaxiality ratio -1, with the principal axis inclined at 45 degrees. So if we were to scale each case using two unrelated loading histories for the tension and torsion, and then superimpose them, the resulting stresses will have a biaxiality ratio that varies between -1 and 0, and principal stress directions that rotate. So this is a non-proportional loading. We have a varying biaxiality ratio and or a varying orientation of the principal stress tensors. That's non-proportional loading. So to sum up, non-proportional loading implies that either the biaxiality ratio or the principal stress directions, or both, vary with time. Otherwise, the loading may be multiaxial, that is not uniaxial, but is proportional. And so pure shear and equibiaxial are special cases of proportional loadings where the principal stress directions remain fixed and the ratio also remains fixed. Okay, now the case described on this slide is very important because it shows how multi-axis loads on a component do not always lead to multi-axial loadings, that is, multi-axial stress state variations. So let's take the hollow cylinder from the last example and we'll introduce a hole into it. Now, the critical location for fatigue in this component is going to be somewhere on the edge of this hole due to the stress concentration. However, if you think about the stress state at the edge of a thin sheet, it can only ever be uniaxial and parallel with the edge, irrespective of what the external loads are. So it's very common in components that the fatigue life is determined by critical locations that are associated with stress concentrations. And these features tend not only to concentrate the stresses, but also to align them, so that the geometry of the component or structure often gives rise to approximately proportional or uniaxial stresses, even under complex external loading. So multi-axial loads on the structure don't necessarily give you a multi-axial loading locally, and if so, it can still be approximately proportional. Okay, so now let's have a look at how the software deals with and measures multi-axiality. First of all, most fatigue problems involve cracks growing from a free surface, or maybe in a thin sheet, and in both those cases the stress state is two-dimensional. This makes our analysis simpler than our visualization of things. For shell models, the stresses are typically already resolved to the plane of the surface. They come out in element coordinate systems. But for solids, we typically have to do this. Actually, DesignLife is set up to do this by default. If you look at the analysis group properties, there are some default settings which are surface nodes only set and resolved to local, both set to true, and these two result in local coordinate systems being defined for every surface node, where the local z-axis is a surface normal, and then we rotate the stresses to this coordinate system. So what this means is that as when we rotate it to that coordinate system, our 3D stress state becomes a 2D stress state. We only need to consider the x and y directions. If we're looking at a tensor, that means that all the terms with a z in them will reduce to 0. Furthermore, the remaining terms, this small matrix here in the red box is symmetric, so the two shear terms are equal. So that means we only need to consider 3 stress components, sigma xx, sigma yy, and tau xy, to get a complete description of the stress state. So once these stresses are surface resolved, we can do what we call a multi-axial assessment. There are a couple of options in the software. I'm just going to describe what we call the standard version. We start with a stress history, which is a tensor as a function of time. So then imagine that we plot the stress tensor at each moment in time on a 3D scatter plot. Now the axes in this scatter plot are the 3 stress components, sigma xx, sigma yy, and tau xy. Every point in the time history generates a point on this scatter plot, and eventually we end up with a cloud of points that represents the entire stress history. The shape of this cloud of points tells us what the stress is doing throughout the loading. Now, if all those points lay on a straight line through the origin, that would represent proportional loading. If we get more of a blob, that indicates a non-proportional loading. In practice, we most often see a kind of sausage shape, which represents a nearly proportional loading. So we look at that cloud and we carry out some statistical analysis on the cloud, and the orientation of the cloud tells us the biaxiality ratio and also the dominant directions of the principal stresses, and the aspect ratio of the cloud, how thick our sausage is compared to its length, gives us an objective measure of the non-proportionality of the loading. Now, in the software, the default settings of most of the analysis engines do this type of assessment as standard, and we can use it to evaluate our results and then decide either interactively or automatically whether we want to make further calculations at that node. So if you look in the results tables, you'll see mean biaxiality, non-proportionality, and dominant stress direction appearing. So we can actually extend this approach to 3-dimensional stresses, but the stress problem now becomes, the stress plot now becomes 6-dimensional, which makes the pictures difficult. The maths is very similar. We have actually done this. We've only implemented it so far for composites, and we figured it was more important for those because fatigue cracking is much more likely to initiate in the interior of components. We've also prototyped it in the frequency domain for those interested in vibration. Okay, so we've now looked at what multi-axial loadings are and how we quantify them. The next question is, why does it matter? Well, fatigue is a process of the initiation and growth of cracks. Cracks start as shear cracks in stage 1 and then tend to transition to opening mode cracks in stage 2. And so a crack is associated with particular orientations and particular modes of growth. These crack growth processes are strongly affected by the stress state and variations in the stress state, both the biaxiality and the orientation. When we do fatigue calculations using the local strain approach, we pay quite a lot of attention to the cyclic plasticity that occurs, and our analysis methods analyze the plastic deformation and try to capture the shapes and sizes of the positions of the hysteresis loops. And this plasticity, unfortunately, is also strongly affected by multiaxiality. So our process that we use for local strain approach, which incorporates rainflow cycle count, identification of the damage with individual hysteresis loops based on the turning points in the time history. This works very well for uniaxial, and we can extend it to proportional, but when we get really multiaxial cases, the plasticity processes are very much affected too. There are a couple of other important considerations as well. Most of the fatigue data that we collect for materials is based on uniaxial tests. So useful multiaxial methods need to be able to work from mainly uniaxial fatigue test data. The other thing I should mention is that some of the multiaxial methods we're going to look at are significantly more computationally intensive than the uniaxial or proportional methods that we're more familiar with. So this is where multiaxial assessment is really useful, as it helps you to determine what method is really necessary to avoid extra computation. So let's have a look now at the normal process that DesignLife uses to do a local strain fatigue calculation. The process starts with FE results and loading information being assembled to give a local strain history. So this is the linear elastic pseudo strain history, which is a tensor as a function of time. From this tensor, we extract a damage parameter depending on which theory we favour. So this could be largest principal strain, critical plane strain. This is something that we can compare to our uniaxial fatigue test data. So for most cases, the most useful parameter to start with would be the largest principal strain. Then we have to identify the damaging cycles, and that occurs through a combination of rainflow cycle counting and notch plasticity corrections to estimate the elastic plastic stresses and strains. And then finally we can go on to calculate damage. So let's consider now how multiaxiality will affect our cycle counting and plasticity calculations. Now, the local strain approach depends on calculating the size and position of a number of hysteresis loops, which we conventionally do by positioning the largest loop using the cyclic stress strain curve and each subsequent strain excursion using the hysteresis curve. So in this case, we find the maximum point of the cycle, point 1. We position that using the cyclic stress strain curve. We then look for the next turning point, point 2, and we use the hysteresis curve now to find that position. If we are working from elastic pseudo strains, then we also have to put in a Neuber correction on each half cycle. It's all based on the turning points, and it's quite quick. There's a useful extension to this process which works for proportional loadings, and it's called the Hoffman-Seeger approach. So this starts from the same point, but now it uses the biaxiality ratio to calculate an equivalent strain based on whatever the cycle counted strain is. The plasticity and notch correction is now carried out based on the equivalent strain and stress. And then when that notch correction has been completed, we then convert back to our original damage parameter. So this is actually the default setting in the standard EN glyph. It will works pretty well for any proportional loading, including uniaxial. However, when we get to non-proportional loadings, everything gets a bit more complicated. Before I get on to non-proportional loadings, let's just recap a little bit and look at the stress-strain response that we see in a material under uniaxial loading. So let's consider this first plot at the top left of this slide. If we start from 0 and then we increase the load past the yield stress at point A, the response becomes nonlinear and will proceed up to point B. If we unload at point B, we unload into the elastic region. And if we reload again, we'd find that the yield point had moved from point A up to point B. This is called hardening. If we unload all the way down, right back to 0, and then continue into compression, eventually we'll hit the compressive yield point at point C. However, what we find is that the compressive yield point has reduced. It would have been further down, but it's reduced due to the hardening that's occurred in tension. This is the well-known Bauschinger effect, which says that if you yield and cause hardening in tension, then you're going to see a reduction in the compressive yield. So that's a one-dimensional treatment. For multiaxial loadings, we have to replace the yield strength by a yield criterion. Now, if I just consider a really simple biaxial case where I've got two principal stresses, sigma 1 and sigma 2, the von Mises yield surface can be represented by an ellipse. So if we consider what happens when we apply loading to this now, if we load in the sigma 1 direction and cause some yielding, when hardening occurs, the yield surface moves. This is called kinematic hardening, and it predicts the Bauschinger effect, because when we drag the yield surface to the right, then what we've done is we've increased the tensile yield, but we've reduced the compressive yield. So kinematic hardening actually predicts the Bauschinger effect. If we want to do multi-axial loadings, we need a three-dimensional plasticity model that incorporates kinematic hardening. Isotropic hardening will not do for fatigue. We need a kinematic hardening rule. There are a number of these. There are lots of different theories. For example, the Mroz-Galrud model that we had implemented in FE fatigue, the Chabosh model, variants on this appear in Abacus, and in DesignLife we have this Jiang-Suhitoglu model, which I'll talk a little bit about later. For non-proportional loadings, another issue is that the material response is now path dependent. That is, we can no longer do our plasticity just on the turning points in the history. We have to consider the full loading path. And unfortunately, this also means that we no longer necessarily get closed hysteresis loops. Okay, so that's a little bit about plasticity. Let's now think about multiaxial fatigue damage. There are many multiaxial fatigue damage models. You'll find many in the literature. The best ones, in my opinion, are mainly based on the idea that fatigue cracks in ductile materials tend to initiate as shear cracks, which then have to overcome microstructural barriers before they can lead to failure. Now, these little shear cracks are driven mainly by shear strain and grow on planes of maximum shear. But the opening load on this plane is also important, as the potential for damage is increased as you open a crack. So these ideas were worked on by people like Brown and Miller, and I've put just the Brown-Miller equation in here, which it basically combines the shear strain on the maximum shear plane with the normal strain on that shear plane. We'll look at a further development model of this later. and there's the, you can see there's the Wang-Brown the Brown-Miller parameter S there as well. Another well-known model is the Fatemi-Sosi approach. This is using the shear strain on the critical plane and the maximum normal stress to quantify the opening load. If we go to fatigue limit criteria, such as the Dang-Van criterion, the Dang-Van criterion again is using a combination of shear and opening. The shear in this case is defined by the microscopic shear stress in individual grains, and the opening effect is captured by the hydrostatic stress. Hydrostatic stress can't cause plasticity, but it can open cracks. There are some other models as well. For instance, the Sosi-Banantine model. This is based on normal strain and stress, and it may be more suitable for cases which are dominated by opening mode cracking. So following on from the last slide, the state of stress is really important because it affects the orientation of the maximum shear planes. And since cracks tend to grow fastest in mode 2, it also affects the direction of the fastest growth of those shear cracks. So imagine that these little cubes on the left-hand side of the slide here are cubes that have been taken out of the surface of a material. So the shaded surface is the free surface of the material. We're going to look at three different cases. Case A loadings are defined by negative biaxiality, and in this case, shear cracks will be driven fastest along the surface in mode 2. On the other hand, if you've got a positive biaxiality, case B, the fastest direction of growth is on a 45-degree plane inclined and into the surface. Uniaxial loading is a special case in between. Furthermore, if we have a non-proportional loading, we may switch between case A and case B, and the orientations of those planes may also change with time. And under those circumstances, we may have to make more calculations in order to try and identify or to search for a critical plane, one accumulating most damage. Okay, so that's a quick overview of some of the issues that we have to address. The next few slides are talking about the implementation of multi-axial methods in DesignLife 11. So here's just a little screenshot showing a fatigue analysis in DesignLife of a multi-axially loaded shaft, a combination of tension and torsion. Okay, so multi-axial fatigue is, I have to emphasize this, that multi-axial fatigue is not a new feature in DesignLife. It has been considered from the very first version. All the features that I mentioned on this page, so multi-axial assessment, Hoffman-Seeger method, different stress-strain combinations, critical plane methods, Dang-Van method, and also a configurable automatic mode which bases calculations on what the state of stress is. All of these have been in pretty much from the beginning. The auto mode is interesting. This takes advantage of the configurability of DesignLife, and it does calculations in 2 steps. In the first step, it makes a fatigue calculation which will be okay in most cases. So typically using the Hoffman-Seeger correction, largest principal strain, Morrow mean stress correction. That works very well for a majority of cases. But at the same time, we also do a multi-axial assessment, and the software will recalculate at each node or element depending on whether the the state of stress, the biaxiality ratio, and the non-proportionality factor, tell it that a better approach, such as a critical plane approach, should be used. So that has been in pretty much since the beginning. So the question is then, what is new in version 11? Well, the multi-axial DesignLife engine has been in there for a few versions too, but as a beta version. Version 11 is migrating to being fully supported. We've made improvements to the plasticity and notch correction, various fixes and documentation improvements. Also included in the release, there's a pre-configured multi-axial DesignLife glyph. This works in a rather similar way to the auto mode mentioned on the last slide, except that it uses the multi-axial EN engine now for the most non-proportional cases, which it's going to handle better than the standard EN engine. And that's due to the fact that it's got more sophisticated plasticity and damage modeling. We've also tweaked the settings on this glyph for better performance in version 11. There's also a new worked example under development that will be available shortly that takes you through the capabilities of the engine. Now the analysis process is a little different from the standard EN engine because of the need to address path dependence in the material stress strain response. So you can no longer just work from the turning points. So the process starts off by assembling the elastic pseudo stress history based on the external loads and the FE. And then this information is passed through the notch and plasticity models to predict the local stress and strain history. And this is the full stress and strain history, not just the turning points. And then finally, we push those local stresses and strains into the damage model and calculate the damage using the Wang-Brown multi-axial rain flow and damage model. I'll give you a bit more detail about that in a minute. If you don't want to rely on the on nCode to do the notch plasticity, and if you have a relatively short and simple loading, it is possible to simulate the elastic plastic behavior completely in the FE. So use your nonlinear FE. Using kinematic hardening, of course, you can predict the local stress, elastic plastic stress strain and stress history directly, and then go straight to the fatigue calculation. So let's look then, first of all, at the notch and plasticity modeling. The notch modeling scheme that we've got in DesignLife is based on a method proposed by Young-Lee Lee, who's now at Chrysler. And this separates out the notch correction from the plasticity model. So it starts out by using a notch correction such as the Neuber method, but applying it to the material stress strain curve and using it to predict a new stress strain curve, which is an elastic pseudo stress versus local strain curve. We then use that curve to initialize the plasticity model. And what we've done is we've turned the plasticity problem in the notch problem into a plasticity problem. So we then push the local pseudo stress history through that plasticity model, and out pops an estimated local strain history. If we also want the local stresses, we have to reinitialize the plasticity model with the original stress strain curve, and then push the local strain history through that to get the local stresses. So the next slide just looks a little bit more at this first step, the application of the notch correction. So this is illustrating the calculation of the pseudo stress local strain curve. So what we do is for a number of elastic pseudo stresses, we carry out a Neuber correction. That's graphically illustrated by searching for the putting a rectangular hyperbola through each of those red points and seeing where they intersect the uniaxial cyclic stress strain curve. So that gives us a set of estimated local strains corresponding to the pseudo stresses. If we then plot those a curve of pseudo stress versus the estimated local strain, we can refit another set of Ramberg-Osgood parameters to it, and we get a new curve. We can use that to initialize our first run through the plasticity model. The plasticity model currently implemented in DesignLife is the Zhang-Sahitaglue model. It's a rather sophisticated model. So it's got kinematic hardening. It uses multiple back stress components to capture the material memory effect. And it's also capable of capturing effects such as ratcheting and non-proportional hardening, though you do need some additional parameters that you have to modify in order to capture those effects. Most people won't have access to that kind of test data, and so we've set it up in such a way that it will work using standard uniaxial strain life parameters. Works pretty well, but it's quite computationally intensive. We're also at the moment working on implementing the Ross-Garud model, which is a bit simpler and should be computationally more efficient. Okay, so how well does it work? What I've got on this slide is a validation case for this combination of notch plasticity and plasticity and notch correction. And it's based on an example from the literature. So it's taken from the work of Barkey and partners. It's based on a notch shaft which is subject to an out-of-phase torsion and tension loading. So we get a highly non-proportional stress state at the notch root. And what I've done here is to compare the measured axial and shear strain response measured at the notch root from the publications and comparing it to our estimate of the axial and shear strain at the notch root using the Zhang-Sahitaglue model and combined with either the Neuber or Glinka notch rules. And we've done this for 2 different load levels. So all our calculations have been based on uniaxial material data here. So this is the first load level. The black line is the experimental load path. The red line is using Zhang-Sahitaglue and Glinka, and the blue line is using Zhang-Sahitaglue and Neuber. And you can see that they both do a reasonably good job of estimating the stress-strain response, with the Neuber method being a bit more pessimistic, as you might expect. That's just the same calculation, but done with a higher loading level. So that's just one example showing that it works quite well. Okay, so this is the calculation implemented in DesignLife, and this example actually forms the basis of the new multi-axial worked example that I'm working on. When it comes to damage modelling, we've selected what we think is the best damage model available, which is the Wang-Brown method. This method's evolved from the Miller-Brown approach that we mentioned earlier. So it's based on a combination of the shear strain on the critical plane and the maximum normal strain on the critical plane. However, the Miller-Brown method was for proportional loadings only. So it doesn't work for non-proportional loadings. And what Wang-Brown have done was to develop an extender model to apply to non-proportional loadings. And they've done this by introducing a multi-axial rainflow cycle counting procedure. They've also added a mean stress correction, which is similar to MORO, but based on the mean normal stress on the critical plane. And what this method does is it takes the concept of rainflow cycle counting, but it extends it to multi-axial loadings using the von Mises yield criterion. So what you do is you identify the largest value of the von Mises yield criterion that occurs during the loading history, and that is your maximum turning point. So from there, that you unload elastically and you search for the biggest value of the von Mises strain based on the strain relative to that first turning point. So it's kind of an iterative process where you walk through the history looking for the loading and unloading points as you would in normal rainflow counting, but this time taking into account the full 3D stress state. So in this method, you find a whole series of reversals, and for each reversal you look for the plane with the maximum relative shear strain, which defines the critical plane. So each reversal potentially has a unique critical plane, the plane of maximum relative shear strain, and we accumulate the damage from all reversals. So it's all been formulated in such a way that for a uniaxial case, it reduces to the usual Coffin-Manson-Baskin equation. The only extra parameter you need is this Brown-Miller parameter, S. And in the software, we've defaulted that to 0 for case B loadings and 1 for case A. You can change it, but the defaults give reasonable values. And the software identifies automatically whether each reversal is a case A or case B reversal. So all this goes into the multi-axial EN engine. This is a rather boring screenshot of the engine properties, but you will notice that there are some extra properties at the bottom which allow you to tune the behavior of the plasticity model. Now, the multi-axial fatigue engine is a bit more computationally intensive than the usual calculations. So if you have a large model and a long loading history, it may not be wise to run it on the whole model, but to use it in a smart way so that you only apply the multi-axial EN engine to the most non-proportional cases which need it. So what we've done in the software is to provide you with a pre-configured glyph that does this for you. It's set up to work in a very similar way to the auto modes in the standard SN and EN engines, but for the most multi-axial cases, for the most non-proportional cases in particular, it will use the multi-axial EN engine. So that's when the non-proportionality factor is over a threshold value. It's all user configurable, so you can change the configuration. But one thing you should avoid doing is applying time history compression on this last step, because remember that the plasticity model and the Wang-Brown calculation, the stress-strain response and the damage is path dependent. So if you do peak valley slicing, you'll change the loading path. Okay. The next slide shows you how the configuration works. It's a multi-pass analysis. In the first pass, we use the standard EN engine with sensible default settings, and it also does a multi-axial assessment. It then uses a number of elimination post-processors to categorize the nodes and elements into subsets according to what the mean biaxiality ratio and non-proportionality factor is. And we then use some Boolean operations to combine these subsets for processing, if necessary, in one of another 5 runs. In the final run only, for the most non-proportional cases, we use the multi-axial EN engine with the Wang-Brown and Jiang, so heater-glue methods. And then the final results are collected together in the results table. And one of the important pieces of information that we include in the results table is the run that has been used for the final calculation in each node. So if you look at this table here, we're in the column results source, you'll see that the elements listed have been processed in run 6 using the Wang-Brown method. So they were the most multi-axial ones. Okay, so to give you an idea how this works, we've taken some results again from the literature. This is from the SAE shaft test program. This notched shaft was tested in combined bending and torsion with a variety of proportional and non-proportional loadings. So the first plot is a plot of predicted on the vertical axis with design life and experimental life on the horizontal axis. So perfect correlation would have a straight line. The dotted lines on here are the plus or minus factor of 3 scatter band. There's always scattering fatigue data. In this case, the correlation is not bad, but there are a few points that fall on the non-conservative side of the line. So this set of points here that I'm showing was calculated using the standard EN engine with the auto multi-axial mode. So this is what's been available up till now. If we look more closely at those results, we see that those ones that are above the line are from non-proportional loadings. Now, if we rerun all the same examples now, this is with a range of non-proportional and proportional loadings, but now using the new configured multi-axial glyph, these non-proportional cases are going to be analysed using the multi-axial EN engine. So the correlation now is represented by the crosses on the plot, and what you can see is that the points that were falling on the non-conservative side have now been brought either into or much closer to the plus or minus 3 scatter band. So we get an improved calculation. Okay, so a few concluding remarks. It's not always necessary to use multi-axial fatigue methods. In some circumstances, it is. So in DesignLife 11, we've provided a range of multi-axial fatigue methods for both low and high cycle fatigue, for both proportional and non-proportional loadings. And the configurability of DesignLife allows you to apply the more sophisticated and computationally intensive methods only where necessary. So that smart approach allows us to achieve a good combination of accuracy and efficiency. Okay, and that concludes the webinar. Thank you very much for listening.